Welcome to this experiment on lateral displacement due to a glass slab. So we have in this experiment a glass slab, and what we're going to do is we're going to keep this glass slab here and have a light ray pass through this glass slab. So ideally this ray would have gone straight. Now because of this glass slab, you will see that the light ray or light beam gets shifted, and that's due to the refraction, and the distance between these two rays are called the lateral displacement or deviation. So for this we need we have marked all the all that we need. So here we have, imagine that you have this glass slab. So we have drawn these two parallel lines for the glass slab, and we have also marked our normal, which is 90 degrees to the face, and then you have these different incoming incident rays we have marked, and we have marked it such that it exits outside. And in this small setup we have a light box. So this box, it can produce a simple light beam onto this paper, so you can see that. So that's a simple light beam. So here I'm going to now see how this beam is manifesting in this with a glass block, right? So first let me align this beam into this incoming beam into this line. So you can see it's perfectly aligned, and once I do that, I keep this glass block. So I keep this glass block exactly in between these two parallel lines. So you can see that there is almost no deviation. So I'm going to mark my exit. My exit beam is over here. So I'm going to mark 2 points, and later I'm going to extend these 2 points to get my exit line. Okay, so now let's do the second one. So I'm shifting the angle of incident to 15 degrees. So as I keep the angle of incident as 15 degrees, you can see that, hey, this is a partial reflection and refraction, but yeah, due to refraction the exit rays have shifted. So I'm going to mark these 2 points indicating the shift. Later I will join them. And now let's look at 30-degree angle. So for 30-degree angle, you can see that I have to shift this glass prism slightly. Okay, so I have the exit points here and another point here. So let's do it now for 45 degrees. 45 degrees is here. So I shift my angle, so I align it to 45 degrees, and I see that the exit rays are here and here. And let me now do it for the final one, 60 degrees. It's a bit tricky because light has to travel much longer distance, so you may not see the exit. Let's see if I can get it. First align these rays, okay, and then I put this glass slab here. Oh, we're lucky we get it. So we have this very, very weak, you can see this light ray extending. So these are the 2 points, all right? So all I need to do now to get my refracted ray is join these 2 points. So this is my refracted ray. So internally the light should have traveled like this for it to have come out that way. So here I have marked the refracted ray, and you can see that more or less these two are parallel. So maybe you can't see it's in the edge. So let's do for the next one and see the lateral shift. So you can see it meets here. It should have come like this. So there you go. So here you can see it's clearly these two rays are parallel. Let's do it for 30 degrees. Okay, and there you go. And finally for 15 degrees. you can see the shift is very less. You can see the shift is really less. And finally, you will see that for I is 0 degrees, there is no shift. It just goes straight away. So this is an experiment. And now what we need to do is to draw normal and measure each of the angle. So I'm going to do that and see how the angle, how these angles are they same as this. So we're going to check that. So here you see that we have joined these lines, and once we join the line, we have measured the different angles. So your incident was 50, and we measured the outgoing angle with respect to the normal, and we see that that's also 50. So we mark that 50 degrees, and along with that we also measure what is your refracted ray. So the refracted ray, you can see, is about you have to keep it like this because it's with respect to that. So you see that that's about 28 degrees. That's 20 and about 8 degrees, you see. So that's 28 degrees here, and the same you can verify if it is 28 degrees. So you can keep it here, and you can see that that's indeed 28 degrees. So that's 28 degrees. And once you do that, you can find the lateral shift by how much this ray has shifted. For that, I can draw a perpendicular line between these two parallel lines. So I drew a perpendicular, and once I draw the perpendicular, you can measure using your scale on how much is the shift. That's about 2.6 centimeters. All right, so let's do this for the last ray, which I have not done. So I thought I'll do it with you. So here is the first thing that we do. We exit normal. We draw the exit normal. So all measurements can be done with respect to that normal. So here is the normal. That's the normal for you. And once you have the normal, then we can indeed find what is the exit angle. And the exit angle we can see is close to 15 degrees. That's about 15 degrees. 15 degrees. You can find the refracted ray angle. And the refracted ray angle you can find by keeping a protractor here. That's about 10 degrees. You see, it's about 10 degrees. 10 degrees. And similarly, you will find with a minor, you will find that that's also close to about 10 degrees here, 10 degrees. So this is your 10 degrees, right? And to find the lateral shift, I need to draw a perpendicular to the exit ray and find where it meets. So that's a perpendicular. So I draw my perpendicular here. That's a perpendicular line, and once I do that, I can find the distance, which is the shift is about 0.6 centimeters. So this is about lateral displacement is 0.6 centimeters. So you can clearly see that as the angle of incident is increasing, the lateral displacement is also increasing. And also you can see the refracted angle is also increasing. So here is a table. We have recorded all the incident angle and the refracted angle. And with this we know that you can apply Snell's law and say that n glass is sine I by sine R. So we're going to calculate the various values of sine I by sine R. So here, let's do it for 50 and 28. So sine 50 divided by sine 28, and that's equal to 1.63. 1.63. That's the refractive index. And next one is sine 45 divided by sine 26. That's, oh wow, that's pretty close. 1.61. The next one is sine 30 divided by sine 18, that's 1.62. Sine 15 divided by sine 10. Oh, that's far away. So we know that that's an outlier, 1.49. And this one is, you can't do this because sine 0 by 0 is sine 0 is 0 by 0, doesn't make sense, so you don't use this. Now this one is an outlier, so usually we don't need to take this for our average calculation. We'll take the best of the three values, 1.63, 1.61 and 1.62. So the average refractive index would be equal to 1.63 plus 1.61 plus 1.62 divided by 3, and that's 1.62. So that's your average refractive index, and that's very close to, we know that that's very close to the refractive index of glass. So this may be a different kind of glass, that's why we get 1.62, but usually you know that N glass is 1.5. So this may be a different kind of glass which have refractive index of 1.62. So thus you can find even the refractive index.